Now that we've seen ways to construct the inverse matrix for matrix A, or the way to develop the matrix that represents the inverse transform, if we're thinking about transforms, it's relevant now to talk about some properties of this inverse matrix, and here we're putting it in the context of matrix multiplication. So the most fundamental property around the inverse matrix is similar to the inverse function. The idea is if that we apply A and then apply A inverse, nothing happens, or we multiply by 1, or in matrix world, we multiply by the identity matrix. And the rationale for that is we know that if we start with a vector x and we multiply by A, that's the same thing as taking the transform of it. And then if we multiply that by A inverse, we have to get back to x. But we also know that the only other matrix that if I multiply x by this matrix and I get x back is the identity matrix of size n, matching size to whatever the vector x is. And so from that we get the immediate equality that A inverse times A has to play the same role as the identity matrix. Now we could derive the second relationship, which is simply that the order doesn't matter, whether it's A inverse then multiplied by A or A multiplied by A inverse. That can be intuited from our idea of functions and inverses, that order doesn't matter. But we can also prove it in a different way. Let's build a y vector, which is the output of our transform. And then we will gradually make changes to this. So what we're going to do is multiply both of these in front by A inverse. So y is equal to ax, and that maintains the equality because we've done the same thing to both sides. Then we use the property from the last equation that A inverse times A can be replaced by the identity matrix. And then we can multiply through, well actually let's tidy up. In times x is the same thing as in times x is just x again. So A inverse times y is the same thing as x. And then what we're going to do is pre-multiply again by A now. So we'll have A times A inverse y equals A times x. But wait, we said that ax was equal to y in the first place by our definition. Don't need that equal sign there. And so what we have is the same scenario as up here. We have A times A inverse y is the same thing as y. And the only thing that works there, or that has that same structure, is the identity matrix times y equals y. So we must have A times A inverse also equal to the identity matrix. Now this last statement here is interesting in the sense that it seems like an easy way to help us solve systems of equations. So this is a system of equations. This is any linear set of equations, n by n. So n equations and n unknowns. And when we have that scenario, if there is an inverse, then we can solve for x. Our goal is to find x when we have these equations set up. Well, if that's going to be our goal, sorry, I should add little bars here to the x's and b's there. If our goal is to find x, well, what we can do is take this equation here and pre-multiply it by A inverse. So let's call this equation 1, and we'll take equation 1 times A in front of each term. Sorry, A inverse in front of each term. So we would get A inverse times A times x equals A inverse times b. And from the property we derived up here, the A inverse times A is just the identity matrix, which can just disappear, and A inverse times b, the solution to our system of equations. System of equations. All right, now it's probably too early in most of your careers to get excited by this, but once you take a numerical methods course, typically in second year for most programs, you'll find out that this is one way to solve a system of a linear equation, but it's almost always the least, not the least, it's not the most efficient and it's also not the most, I'm going to say accurate here. It's something a little subtler than that, but it's the most prone to round off error and some other things. So really, you're going to want to use RREF most of the time, or instead. But the reason for that doesn't come out of the math here. It comes from the way computers work and how floating point numbers are represented. So way beyond what we're talking about in linear algebra. But just know that this inverse idea is a nice conceptual way, and sometimes that's the way it is just most helpful to be able to think about it. If we have a system of equations with a matrix A, we just find the inverse and multiply that by B. But just know that in practice, when you're solving large systems of equations, and in some of the classes I've been involved with, we solve 10,000 equations at a time, you don't want to have to find A inverse for a whole bunch of reasons. It's more efficient to use RREF, but just know that the alternative is there.